Hello everyone. I am delighted to have the opportunity to present our work on pre-training language model for automatic speech recognition. With the rapid development of smart IoT devices, automatic speech recognition (ASR) has become the standard modern interaction technology between humans and machines. However, as the deployment environments are highly diverse, the performance of ASR systems usually face much lower performance than in the development environment. Robustness is a long-standing challenge for automatic speech recognition (ASR) as the applied environment of any ASR system faces much noisier speech samples than clean training corpora. There are three kinds of major factors that cause performance deterioration of Chinese ASR systems. First, environmental noise usually taints speech signals received by a microphone, distorting the speech piece to an erroneous one. Second, different speakers can pronounce words differently compared to the standard pronunciation in lexicon and training data, which can also cause misclassification in ASR. Third, there are many polyphonic words with identical pronunciation in Chinese language, so it is much more difficult to distinguish the correct one from the candidates, especially when the speech is tainted. For example, with an audio whose semantic is "I am from Guizhou province and I go to school in Guyang was degraded by noises when the speaker said the word Guyang Tuo, a city in China. Fed with this affected speech, the acoustic model may output a wrong phone sequence as Watu, which is more likely to be Mandarin fish Guiyu or belong to Guiyu instead of the correct word Guyang Guiya. The industrial ASR pipeline typically consists of two major parts: the acoustic model (ADM) translating a speech wave to a phone sequence oral ADIS, and a language model (LN) decoding the AM output to a natural language sentence. Conventionally, the LN decoding process is a two-pass process. A fast but relatively weak LN such as n-gram LN first generates a set of candidates, and a powerful but computationally expensive LN like NNLN selects the best sentence from the candidates. To enhance the robustness of a ASR system, it is reasonable to put our hands on AM or LN. However, due to the wide variety of the speech, training a robust AM is expensive and not adjustable to various deployment environments. In contrast, LM is a desirable choice to address the robustness problem. First, we found that the majority of misclassified words can be recovered from context information if the LM is capable of capturing semantics from the tainted context. Second, we can use transformer as the LN. Transformer is a deep model architecture relying entirely on an attention mechanism to capture global dependencies between the input and the output. It successfully reached a state of the art in translation quality. It predicts a target word based on the source position, the whole input sequence, and the previously generated target words. This mechanism enables the transformer to select a better word according to the context semantic. Therefore, transformer is promising for improving LM robustness on tainted phones in the phone sequence. Third, inspired by the recent progress of the pre-training model on many NLP asks, pre-training is helpful to relieve the problem by introducing a more robust LM that can translate the tainted phone sequence to the clean sentence. Based on the above observation and analysis, we propose a novel phonetic-semantic pre-training framework, which integrates state-of-the-art LM architecture with techniques of pre-training and self-supervised learning. The LM trained with PSP can successfully translate the tainted phone sequences into correct sentences. Our proposed framework eliminates the need of parallel speech-to-text data, so it can be trained using large-scale text-only data for pre-training. To simulate the realistics in Aereo, we introduce a novel phone perturbation heuristics that can effectively generate tainted phone sequences from a standard phone sequence as realistic as generated by a non-robust AM. Combining with all these techniques, our PSP finally achieves state-of-the-art performance onto different Chinese datasets with several domains. Next, I will introduce the model architecture of our LM in detail. To demonstrate our effectiveness and control the variables, we adopt the AM from an existing ASR model and fix it, which also represents an ordinary AM used in real-world applications. We focus on the development of the PWT module containing phone embedding M, encoder enc, decoder deck layer, and in a fine layer W, the phone embedding layer maps the phoneme index to a dense representation, and the encoder encodes and captures information from the phone sequence. The decoder outputs corresponding representations of predicted words. As PWT is designed to tolerate tainted phone sequences, the encoder should capture the semantics from the context that can recover the polluted phonemes. Thus, we design an affine layer W that maps encoder output space to the phone embedding space. Inspired by the learning mechanism in human intelligence, which learns skills gradually from easy to challenging tasks, we train the model with noise-aware curriculum learning by dynamically composing two objectives. The pre-training process consists of 3 stages: warm-up, self-supervised learning, and fine-tuning. In the warm-up stage, we use a clean phone sequence translated from text only, aimed at initializing the basic embedding and model parameters for learning the mapping between phone sequences and words. In the training stage, we gradually increase the learning difficulty from 2 aspects. First, the data are noisy. We use a tainted phone sequence produced by the empirical phone-perturbation heuristics. Second, the training objective is more complex. In the fine-tuning stage, we fine-tune the model with small in-domain data. The benefits of noise-aware curriculum learning are explicit, as the parallel ASR corpus are precious and limited. The pre-training step warms up the model without the need of parallel data, providing faster and better convergence of the PWT model. To simulate the practical errors in phone sequences caused by AM, we design empirical phone perturbation heuristics consisting of 3 operations on clean phone sequences, i.e., RE replacing the selected phones with others, DEL deleting the selected phones, and INS inserting randomly sampled phones. The heuristics work on each phone sequence as shown in the following steps. First, sample K perturbation operations mentioned above with replacement. According to the statistics in real-world phone errors produced from AM, the replacing errors account for around 75 of 3 kinds of errors. Therefore, we simulate a similar sampling ratio on 3 operators. Second, sample a starting index and a tainting length L from a Poisson distribution. Third, we conduct corresponding perturbation operations along with their starting indices and lengths. The PWT pre-training is a combination of supervised learning and self-supervised learning with the unlabeled text accessible from everywhere. Given a plain text Chinese sentence, we first segment it into words and then convert them to their standard phone sequences according to a lexicon. There are 2 objectives for training the PWT: translation and tainting recovering. The first objective enforces PWT to learn translation from a phone sequence to a word sequence. As shown in the first equation, YIT is the TTH word in the ITH ground truth sentence, and YIT is the corresponding prediction. The second objective leverages self-supervised signals by randomly perturbing alpha% of phonemes in a phone sequence, enforcing the encoder to recover the tainted phonemes according to the context. Therefore, the encoder is encouraged to capture the high-level semantic information of the given sequence, as well as the fine-grained phone token representation. This objective encourages the model to learn a recovered embedding T that close to the clean embedding and distant to the tainted embedding. We compare our proposed framework with the SOT-ed industrial hybrid ASR system, called chain model, abbreviated to chain. To further probe how our framework takes effect, we conduct an ablation study as well. We note PSP as the bare PWT model, i.e., only training with datasets in state I. PSP data stands for training the PWT model with phone perturbation heuristics. PSP LT R introduces the tainting recovering objective, i.e., self-supervised learning in stage II. To show the effectiveness of fine-tuning, we also compare all models after training with in-domain data. We use the suffix FE to represent the fine-tuned model. This table summarizes the CER results of various models on insurance and electronics datasets, which shows that the complete PSP framework achieves significant improvements compared to the baselines. More specifically, comparing chain model with PSP model, whose source are 22.94 verses, 22.71 and 23.29 verses, 22.50, we find that the encoder-decoder architecture itself does not bring huge improvements less than for without tuning with in-domain real data. However, the improvement of PSP-FT against chained FT is significant more than 20, which means when fed with real data, the transformer's capability of capturing complex contextual information becomes notable. We can also conclude that the tainting recovering objective plays an important role in the PSP framework. To examine the robustness improvement of our proposed framework, we synthesize a real-world mixed-domain testing set with different levels of signal-noise ratio (SNR). The testing set is composed by clean Chinese speech collected from domains including insurance, electronics, finance, and so on. The noise is injected into clean speeches using Kaldi to simulate a real-world noisy environment. When SNR is zeroed, the magnitudes of noise and speech signal are equal. The larger SNR value stands for the cleaner speech data. Tables 2 and 3 show the CDR scores of the baseline model and our proposed PSP model under different SNR conditions, as well as the mean CDR and the standard deviation. When SNR becomes smaller, meaning that the input speech is cleaner, both models have better CDR, and our PSP model significantly outperforms the Kaldi chain baseline. Under the extremely noisy conditions, our method has a larger advantage. Comparing Table 3 to Table 2, the fine-tuning improvement of our PSP model is larger than the baseline. This figure shows that with phone perturbation heuristics, our model is able to correct a chauffeur y-vantwo supply of goods to a chauffeur y-vantwo membership according to the context, even without real data fine-tuning, while the Kaldi chain model fails to recover it even after fine-tuning. This figure represents a kind of bad case where AM generates additional phones, which causes unreasonable results. In this case, the speech is introducing a mobile phone with the best camera quality. However, the erroneously inserted phone D if low turns the result to this mobile phone is the best of low camera pixel. The PSP EA limited model successfully fixes the redundant phone of 5 and turns D if low to L if in, avoiding changing the speech semantics. With finer tuning, the errors are completely removed. This figure shows a compounded case, where some phones are missing in AMO. Therefore, the chain model and the bare PWT model fails to generate a valid sentence. With in-domain fine-tuning or phone perturbation heuristics, the bare PWT model generates a valid sentence but still misses the word simye xing furby eat wo gender. While with complete pre-training and fine-tuning, the severely tainted speech can be correctly translated. It is worth noting that when a long-range continuous phone sequence is missing, all of the models fail to recover it. In this work, we propose a novel pre-training framework, dubbed as PSP, for robust speech recognition based on phone-semantic translation. Our framework includes 3 stages with unpaired text pre-training, self-supervised learning, and in-domain real data fine-tuning. To facilitate the performance, we introduce phone perturbation heuristics and the tainting recovering objective during the self-supervised learning stage. We conducted comprehensive experiments that demonstrate the PSP framework's effectiveness onto large-scale real-world Chinese conversation speech datasets, achieving relative CER reductions of 28.63 and 26.38. It also validates the robustness against noisy speech datasets. Created by Digiteclature.